Hi, everybody. This time we're going to talk a little bit about energy from fuels, and we're talking a lot about hydrocarbons, those mixtures of hydrogen and carbon compounds that we use for in everything from diesel fuel, gasoline, methane, propane. Now, these chemical fuels, where did they get their energy in the first place? Well, this is stored sunshine. The sun shone on beautiful plants on planet Earth for millions of years, mixing with water, and plants breathe in carbon dioxide through the miracle, I think it's pretty miraculous, of photosynthesis. Hydrocarbons are produced and then plants breathe out oxygen. When these bonds are broken through the process of combustion, the hydrocarbons mix with oxygen to produce carbon dioxide, water vapor, and energy as heat. This is the law of conservation of energy, law of conservation of matter, all wrapped up into one pretty little package. And I think this circular cycle of life, energy, and everything on planet Earth is fabulous and one of the most beautiful things you'd ever want to imagine. When you talk about the energy in a fuel, chemists who are older than you and I and smarter than you and I have figured out very precisely how much energy is stored within each specific chemical bond, between two sulfur atoms, between a hydrogen and an iodine, between a carbon and a hydrogen. They know exactly how many kilojoules of energy per mole of each one of these, how much energy is there if you happen to break one of those bonds. With tables like this, chemists are able to calculate exactly how much energy can be released when any one of these fuels is burned. Because when it's burned, this molecule is reduced to its raw material, it's reduced down to its pieces. So let's just, at warp speed, go through one of these situations. Methane, which is natural gas, which we use for cooking, has got a structure like this. So it is 4 carbon-hydrogen bonds. There's 4 of these. Each one of them has a bond energy of 413 kilojoules per mole. So 413. And so there's 1,652 kilojoules per mole of energy that we get out every time we burn methane. That is just a known fact. You take something like gasoline. Now, gasolines are blends. They are blends of between 5 and 12 carbons long. But for simplicity, let's say that our sample of gasoline is completely made out of octane. Well, octane molecule looks like this, and that is 7 carbon-carbon atoms, and each one of the carbon-carbons is 348 kilojoules, so 7 times 348 is going to give us 2436 kilojoules. There are also 18 carbon-hydrogen bonds, and each one of those carbon-hydrogen bonds is 413 kilojoules per bond, and that's 7,434. We add those together, we get 9,870 kilojoules per mole. So if we compare that to our old friend methane from the previous page, methane, that little molecule we use in our gas stoves, methane was 1652. So let's divide 9870 divided by 1652. That's 6 times more. Every single octane molecule is going to give you 6 times more energy per molecule that we burn than with methane. It is a bigger molecule in gasoline, and it's got a lot more oomph. You may have had in your life, you may have some people that you love that have whined a little bit when alcohol started being added to gasoline. I don't know about you, but I had people in my life who whined when alcohol was added to gasoline, and they said the gasoline has less energy, has less power. Well, an ethanol molecule is C2H5OH. It is a much tinier molecule, and it is going to, of course, have a lot less oomph than an octane molecule. So if gas is blended so it contains 10% alcohol, I'm not going to go through the math, but if you do, what you end up with compared to it being straight octane, you're going to end up with a 7% energy drop. So your Uncle Ferdinand, whoever it is, who is running around saying, yep, gasoline doesn't have as much power and zip when they added the alcohol, he's right. There is a 7% energy drop per quantity of gasoline because you're burning smaller chains of hydrocarbons. Instead of putting logs on the fire, you're putting small twigs on the fire. And small twigs, a pile of hay, is not going to give you as much heat on your bonfire than a pile of logs. It's a smaller molecule. Now, the longer the molecule, the longer the hydrocarbon chain, the more energy is going to be in that. And that also has to do with where we use them. If we're cooking on our gas grill, we're trying to boil an egg in our house, we can use these small molecules because these small molecules are just fine. We don't need massive amounts of heat if we're just trying to fry a steak. Those are just fine. But if you have to do bigger and more powerful jobs that require more energy, you're gonna need more powerful molecules. And that's why if you're going from boiling a pot of potatoes to driving an automobile, you're going to go from a small molecule to a longer molecule. It's gonna have more oomph. If you are going from an automobile to a jet, you're going to go for a bigger molecule. If you're going from a jet to a diesel, you're going to go for a bigger molecule because it represents more energy per molecule. But wait, look at this. A 747 jetliner can weigh just a little under 1 million pounds. They are huge. When you start loading them with fuel and people and things on the drink cards, they are big beasts. An 18-wheeler going down the road, fully loaded, can maybe be a little under 100,000 pounds. So this is maybe 10 times more powerful. Why in the world would they not use a bigger molecule to power a jet? Why don't they use diesel fuel instead of kerosene to power jets? Well, there's a whole bunch of choices that go into engineering things. What do you have to do with diesels in Wisconsin in the winter time if the truck driver stops for supper? Well, he has to make sure that the glow plugs are plugged in. He's got to make sure that he leaves the engine running. He's got to keep this warm. And where do jets fly? Well, very often they're at 40,000 feet. And what's it like up there? It's cold. So you cannot have fuel at 40,000 feet that's possibly going to turn into gel. And so they're going to pick the largest molecule they can with the most oomph that's not going to solidify on them and turn into Vaseline on them. That's why they're going to use kerosene instead of diesel. Would diesel give them more oomph per molecule? Absolutely. It's going to give them a lot more energy. But there's some practical reasons why you can't use that at 40,000 feet. Diesel works well. That's why it's used in supertankers and trains and trucks. Now, there's another thing that comes into play here, and that is the idea of activation energy. Activation energy is the energy needed to begin a chemical reaction. Now, the best example I have of that is matches. If I have a book of matches, I have one chemical on the tip of the match, one chemical on safety matches, that's a phosphorus chemical. It's usually kind of a dark red color, and it's on the outside of the book of matches, and oxygen in the air. And I've got all of the chemicals I need for combustion. It's easy, but I have to have one more thing. And the thing I have to add is heat. I have to strike that match against something in order to add that spark to make it go. That's called the activation energy. Chemists illustrate this with something they call an activation energy hill. This is the energy of the reactants, the things that are going to react. This is the energy down here of the products. And the amount of energy you're going to get out of the chemical reaction is the difference between where you start and where you end. The problem is, in a lot of chemical reactions, you got to kick them. You got to give them a little oomph to get them started. And that's this activation energy. This activation energy is that hill you got to kick them over. For matches, you got to give them a little bit of a spark. Now, different fuels require different amounts of activation energy. Something like methane in your gas stove, it's a little activation energy hill, tiny little spark. Doesn't take much to ignite methane. It's got a small activation energy. The longer the chain of hydrocarbon, the bigger the activation energy hill. So it takes more and more and more energy to get the reaction started. But the payoff is, once you get the reaction started, the difference between reactants and products is bigger, and you get more energy output. So is it worth kicking it over a little bit more? Yes, but it's trickier. It's a lot harder to ignite diesel fuel than it is methane, but you get more energy out of that reaction once it does start. One of the other cool things that this explains is why old gas is hard to start. Okay, the nemesis in my life is my weed whip. This year for Mother's Day, I got an electric weed whip. I am very happy with an electric weed whip because my gas weed whip has been my nemesis for years. And it's because of old gas. And here's why. Gasoline is a blend, 5 to 12 hydrocarbons very typically. And each one of them has a different activation energy hill. And it goes like this. If you've got a blend of one hydrocarbon, and then you've got another one, and then you've got another one, and another one, because gasoline, remember, is a blend. And you've got all of these put together. Over time, what's going to evaporate first? What's going to evaporate first or vaporize first are those that are the smallest chains, those with the lowest activation energy. When you've got fresh gas is great. Fresh gas means that somewhere in that blend, you have got something with a really small, low activation energy. You put in a little bit of a spark, you put in a little bit of an oomph, and you can start that engine. Because once you ignite these, that power, that is going to ignite all the rest. But what happens is when the gas gets old, these have vaporized. They have evaporated. And if the gas gets old enough, these are gone, and these are gone, and these are gone. And the only thing left in the gas tank are the big honking molecules with the big nasty activation energy hill. And you pull and you pull and you pull and you pull and you pull, and you cannot start it. So only the high activation energy molecules are left. And dickens, that's hard to start. And that is because of the fact that gasoline is actually a blend of hydrocarbons, and those small hydrocarbons are the ones that are going to evaporate or vaporize first. So get some fresh gas. It's a good thing. All right, talk to you later, and we'll come back and start a whole new thing. See you soon. Bye-bye.